This meeting is now being recorded.
Okay, thanks for joining us today. I'm assuming a mixed set of backgrounds, so I want to start with the basics and work up from there to try and include the main things you know, to try and make this a sort of a general tutorial on missiles. The goal is to help you understand not only what countries do when they're developing increasingly capable missiles, but why they do it, at least from a physics point of view. Of course, what countries do also depends on what materials they have and other sorts of engineering details. And I'm hoping to arrange a talk on some of those engineering details later in the year. But for today, here's what I'd like to do, is talk a little bit about the basics of trajectories, move on a little bit to propulsion, and at least for the first part of the talk, I'll talk about liquid propellants because that's really the technology that's relevant to most developing countries. I'll go on to talk a little bit about guidance control, the problems of reentry and heating, and then how those relate to accuracy, because that's obviously one of the things that people care about. Now, from the point of view of all the engineering details that go into a missile, it's a very complicated system. But from a physics point of view and trying to understand what needs to happen, it's actually quite simple. So you imagine having an airframe and some sort of propulsion, a guidance and control system, and a warhead that it carries. And that's basically the model that I want you to keep in mind. There are basically three parts of a missile phase, a missile flight, and just to get the terminology right, the boost phase is the part when the engines are burning. It accelerates the missile. After the engines turn off, the missile is unpowered. It moves under influences of gravity and air resistance. And that's why it's called ballistic. Ballistic comes from the word to throw, and it's like throwing a ball. So you control it until it leaves your hand, and after that it follows gravity and air resistance. And this typically lasts a few minutes. Then it's followed by mid-course phase. For ranges longer than about 500 kilometers, it will go high enough to be above the sensible atmosphere, which typically people think of as about 100 kilometers. And at that point, it's just traveling under the influence of gravity. And I've put over here on the side just to remind you that the atmospheric density is essentially exponential. And so as you go up, it gets quite thin, but it's still, for high speeds, it still can be problematic up at 80 to 90 kilometers. This phase for long-range missiles can last 20 to 30 minutes, and again, we'll come back and talk about that a little bit. And then at the end, there's reentry phase, and that's when the warhead is coming back to the ground. Atmospheric effects are large. It tends to last a couple of minutes, and it leads to intense heating of the warhead and inaccuracy. And again, we'll come back and talk about that in more detail. Just to give you a picture of what's going on here, this is a long-range missile flight. You can see the boost phase and the reentry phase are a small part of this. Most of it is the mid-course phase. The small blue line here is sort of 100 kilometers, the sensible atmosphere. And so you can see that for a long-range missile, it spends most of its time above the atmosphere in mid-course phase. Again, just to give some idea of the terminology that's used, when people talk about short-range missiles, they typically mean shorter than about 1,000 kilometers, so Scud missiles, things like that. Medium-range missiles, typically 1,000 to 3,000 or 3,500. Intermediate, from 3,000 or 3,500 up to about 5,500. And ICBMs, intercontinental ballistic missiles, are consider those by treaties written by the United States and Russia to be missiles with ranges over 5,500 kilometers. And I just point out that 5,500 kilometers is shorter than the distance between the U.S. and Russia, so it's just worth keeping in mind that intercontinental can mean something shorter than that. Another point that I think is clear to most people, but I just want to make it up front, is that range, which is one of the things we'll focus on, not an intrinsic characteristic of a missile. It depends on the payload. One example is if you look at the U.S. Trident submarine launch missile, fully loaded, which has 8 warheads and has a range of about 7,500 kilometers. If I remove half of those warheads, go down to 4 warheads, then the range goes up to 11,000 kilometers. Again, it's fairly straightforward, but it's just worth keeping that in mind because people often talk about ranges of missile without specifying payloads, and in some cases that can matter quite a bit. Now, the main characteristic that you care about with a missile is the range the system can carry some payload to, and to some extent the accuracy that it can deliver that payload to. The range is determined mainly by the speed and the direction when the rocket engines burn out, as I said, just like throwing a ball. So you call that the burnout speed, the burnout angle, and to some extent you're concerned about the altitude, the burnout altitude. I should just point out that for longer range missiles, the missiles are launched vertically and then turn over after that and follow a trajectory. Now, for a given speed, there's an angle that maximizes the range, and that's what this slide shows. If the trajectory is too steep, you get a lofted trajectory, or if it's too not steep enough, you get a depressed trajectory. And in both of those cases, you get a shorter range than an optimum angle in between those two. Now, you can think of that, the longest trajectory here, you can think of that as the lowest speed that will give that range. And for that reason, it's also typically called a minimum energy trajectory. On a flat Earth, the range is always maximized by shooting at 45 degrees. And that means over short ranges, say 500 to 1,000 kilometers, the Earth doesn't curve very much, so it basically looks flat to the missile, and the optimum burnout angle will be about 45 degrees. But for longer-range missiles, you have to take the curvature of the Earth into account. And so here's a plot that just shows you how that optimum angle changes with the range of the missile. And you can see that it approaches 45 degrees for short ranges. Doesn't go exactly to 45 degrees here because this includes a burnout altitude, which changes that a little bit. You'll typically hear people talk about an ICBM of, say, 10,000 kilometers, which is about a quarter of the circumference of the Earth, having a burnout angle, an optimum angle of about 22.5 degrees. And this is where that comes from. You can see that basically on that graph, that's what comes out. So next, let's turn to burnout speed. So we're going to assume now that you're launching at the optimum angle. And then the question is, what speed do you want to accelerate the missile to get a given range? And that's what this graph shows. You can see that for a short-range Scud missile down around a couple hundred kilometers, you're down below 2 kilometers a second. For a 10,000-kilometer range missile, intercontinental range, and again, I've marked it on here, you're up around 7 kilometers a second. And again, you'll hear people talk about, 10,000-kilometer range around that speed. Now, just to give you a sense of what that speed means, keep in mind that the speed of sound is about 1/3 of a kilometer a second. So 7 kilometers a second is greater than Mach 20. So we're talking about very high speeds here. The other speed that's worth thinking about is that if you're looking at orbital speed of a satellite at 300 kilometers altitude, that's about 7.7 kilometers a second. And so by the time you get a payload up to intercontinental ranges, you're approaching the speeds that you need for putting a satellite into orbit. And you can see the fact that this curve bends over like that means that it's asymptotically going to orbital speed because at that point you've effectively gone to infinite distance because you're circling the Earth. But that's also the reason that there's concern with countries developing satellite launchers that they also can use those if modified for long-range missiles. I wanted to put in this table of sort of approximate burnout parameters just to give you an idea of sort of the burn time for typical missiles, the burnout altitude, I'm not going to spend time on this, but I'll make the slides available, so if anybody wants to take a look at this, the slides will be on the page on our website that also has recordings of the seminars. The other useful rule of thumb that I wanted to point out is something that I call the 1/2 rule, and that means if you have a missile that can launch a given payload to a maximum range of R, and if you launch that missile vertically with the same payload, it can carry that payload to an altitude of roughly 1/2 R. You can show that that's exact at short distances. What's interesting is that it holds approximately even for long distances. So again, it's a useful rule of thumb to keep in mind. Now, so far, this has really been about the relationship between speed and range, and now the question is, how do you get a missile to actually do this? So let's talk about propulsion. And as I said before, I'm going to limit at least the first part of this talk to liquid-fueled missiles. This slide shows a sort of a schematic of the inner structure of the German V2 on the top and the Soviet Scud B at the bottom. And you can see that there's a warhead on the front. Behind that is the guidance system. And then there are two tanks, one of which contains fuel and one of which contains oxidizer. And those two things are brought together typically by a pump into the combustion chamber near the back of the engine. And by combining the oxidizer and the fuel, you get the fuel to burn, and that's what then gives you the propulsion. And so again, one of the things that you can see is that the basic structure, while a lot of things has changed, the basic structure of these systems has not changed a lot from the original V2. So how does a rocket accelerate? Well, not surprisingly, rocket propulsion depends on conservation of momentum. And basically what happens is you've got the large mass M here, which is the rocket. You've got a small mass dm, which is the propellant, being shot out of the back of it at a very high speed, VE, which is the exhaust velocity. And by conservation momentum, that causes the large mass to be accelerated in the other direction by a small amount. So again, just by conservation of momentum, you get that the large mass times its small velocity is equal to the small mass times the exhaust velocity. The thrust then, if I divide this equation by dt, the first term becomes m dv dt, which is just mass times acceleration. So that's just the force that the missile body feels. That's the thrust. And from the other side, we see it's the product of two terms, the exhaust velocity and the mass flow rate of propellant through the engine. And so this is a useful way to think about how you're generating thrust, is the product of these two. The mass flow rate's determined largely by the size and the design of the engine. You can change it to some extent by the turbo pumps and other sorts of things, but it's largely determined by the engine. While the exhaust velocity is determined largely by the type of propellant. And again, that's not exactly true. There are things you can do to increase that, but that's largely true. And it's worth keeping in mind that for chemical propellants of the type people use, the exhaust velocity is typically in the range of 2 to 3 kilometers a second. Now, you'll hear a term that people use frequently called specific impulse when they talk about propellants. And the way to think about specific impulse is it's simply related to the exhaust velocity. So it's really the exhaust velocity divided by the 9.8 meters per second squared, the strength of gravity at the Earth. So when you hear people talking about specific impulse, what you really should have in your mind is that they're really talking about the exhaust velocity, and you can see why from this analysis that's the thing you should be thinking about. Now, before I go on to say why that matters, let me just briefly talk about sort of the North Korean missile development program, because I want to use these to illustrate that. At the short end range, there is the Scud missiles, 300-kilometer range, which is essentially a copy of the Soviet Scud, or potentially in some cases actual Soviet Scuds. That was then modified to add some more fuel to get the range up to about 500 kilometers. But again, these are short range. The next step for North Korea was the No-Dong missile, made a larger missile body, a larger engine. What you can see here is the internal structure. So you see in all cases there are 2 tanks, a guidance system, and a warhead. And that has a range of something like 1,200 kilometers with a payload of a little under a ton. From that, they essentially put something like the Scud on a modified version of the No-Dong to get what was called the Taepodong-1, which was used to try to put a satellite in orbit in 1998. But I want to move on to the next one, which is called either the Taepodong-2 or the Unha-3, which is the North Korean rocket that did put a satellite into orbit a year ago or so. In this case, what you can see is that they have built a considerably larger first stage. They have then put a second stage on it, and even a small third stage with a very small satellite on the front end of it. Finally, the other thing that people talk about with North Korea is the so-called Musadon. The Musadon has never been flight tested. So while people have seen this in parades and things like that, it can't be considered operational. It appears to be a modified version of a Soviet submarine-launched missile, and I'll come back and talk about that a little bit in a couple minutes because it's a quite advanced design the way the Soviets built this thing. Based on my calculations, it looks like if this were operational, it could have a range of something like 300 kilometers with about a 3/4 of a ton payload. So with those in mind, then let's go back and see what North Korea did to try and deal with the thrust. And so here you have a table of some of these, 4 of these missiles, and I've compared it then to the U.S. Titan II as an example of sort of a highly performing missile. And what you can see here is that the Scud-B, the No-Dong, and the Taepodong-2 first stage all have the same exhaust velocity. They essentially use the same propellant, the same kind of engine. By the time you get to the Musadon, North Korea has changed the propellant. In fact, let me. So by the Musadon, if it is what we think it is, and we think it's a version of the Soviet submarine launch missile, then they've gone to a more capable propellant, so a different fuel and oxidizer. And what that's done is it's increased the exhaust velocity. So those are the kinds of things that North Korea has done to try and increase that factor. The other piece, as I said, is increasing the mass flow. How have they done that? Well, in going from the Scud to the No-Dong, the No-Dong essentially has a scaled-up Scud engine. It looks essentially identical, except that it's somewhat larger. By having a larger engine, you can see that what they've done is increase the mass flow rate from something like 60. They've essentially somewhat more than doubled the mass flow rate. Now, in going from the No-Dong to the Taepodong first stage, what they've done is they've taken 4 of those No-Dong engines, which they now have, and they've clustered them together. So you've now, simply by putting them together, have 4 times the mass flow, and so even with the same exhaust velocity, you've increased the overall thrust by a factor of 4. So that shows you basically how to increase the thrust. The next logical step would be to try and increase the amount of propellant so that the thrust can accelerate the missile for a longer time. And when you do that, you run into 2 problems. The first one is that by adding propellant, you make the missile heavier, so that the thrust has to lift a heavier missile and is therefore less able to accelerate it. And the second problem is a somewhat surprising result from physics, which is the rocket equation. And here's the way to think about this. Thrust needs to do 3 things. It needs to accelerate the mass of the missile, even in the absence of gravity. It needs to lift the mass against gravity, and it needs to make up for atmospheric drag. Now, if I go back to the conservation of momentum, the equation we had before, and this time I want, instead of essentially differentiating, and in this case I want to integrate it. So I integrated from some initial velocity to a final velocity, which means taking the mass from some initial mass to some final mass. And if I do that integral, I get this equation that the change in velocity, the difference between the final mass and the initial mass, just turns out to be the exhaust velocity times the log of the ratio of the initial mass to the final mass. And that is the rocket equation. Because it comes from the conservation momentum, it's a fundamental limit, and that's part of what makes it so important. Now the question is, why does this matter? And so I want you to consider the following example. For this example, ignore the mass of the payload and ignore gravity. So we have the initial mass, mi, which is the mass of the structure plus the mass of the propellant that it's carrying. And you have the final mass, which is the mass, just the mass of the structure, because you've burned up the propellant mass. And so if you put that in, you'll see that the change in velocity that you can get from this is equal to the exhaust velocity times the log of 1 plus the ratio of the propellant mass to the structural mass. Now, what that means is in this case, the delta V depends only on this ratio of the structural mass to the propellant mass. Now, one way to try and increase the range is to add propellant. As I add propellant, that makes the missile heavier, and that makes the forces greater. And so you have to scale up the structure because of the additional forces. And what this tells you is that if you scale both the propellant and the structure up by the same factor, you don't gain any velocity. So all of the additional propellant you've put in, the benefit of that is eaten up by having to accelerate the additional structure. So that's why this ends up being an important limit. It means that if the structural mass grows in proportion to the propellant mass, the bigger missile that you have will have the same speed and energy. And that means the structural mass of a missile is a particularly important parameter. So let's just look then at the evolution of North Korean missiles, and you can see here what's happened. How do you reduce the structural mass? Well, for short-range missiles, it's actually fairly easy to get the kinds of speeds you need to get shorter ranges, and so you don't have to worry much about structural mass. The Scud in particular was built to be very rugged because it's going to be a mobile battlefield system. It has a high structural mass. It has a steel body, and so you can see that for the Scud, this ratio of MS to MP is almost 0.3. Now, in the no-dong case, you still have a steel body, but it's less rugged. More emphasis was put on trying to reduce the mass where possible, and you gain from the larger surface volume to surface ratio of the fact that the tanks are bigger, and so that by going to the no-dong, they were able to reduce this ratio by essentially a factor of 2. By the time you go to the Taepodong 2 or the Unha first stage, at this point they've begun to make the body out of an aluminum magnesium alloy, which is lighter than steel. By having a better guidance system, they are able to use smaller fins, which reduces the mass. There's a large surface-to-volume ratio. At the same time, it needs to be strong enough to carry this much larger amount of fuel, and so you're able to squeak out a little bit of an advantage and get this ratio down to 0.11. But you can't get the kind of advantage you might think you could get by going to this lighter construction. On the other hand, by the time you go to the Musadon, and I was talking before, the original Soviet design for this was a very clever design that used lightweight materials. It was a design that reduced the length and therefore reduced the sort of structural mass you have, and you're able to further reduce this ratio down. By the time you get to the Titan II, which I was saying is a U.S. state-of-the-art missile, essentially by using very fancy materials and other sorts of tricks and really making sure that you're getting rid of all the mass that you don't want, you're able to get this ratio down to a much lower number. And just to give you a sense of how much that matters, this graph shows basically the delta V divided by the exhaust velocity. So this is how much of a multiplier you can get over and above the exhaust velocity from the rocket equation at these various ratios of the structural to the propellant mass. And you can see for something like the Scud, sort of the theoretical limit in this case is the total velocity gain can only be about 1.5 times the exhaust velocity, where for something like the Titan II, you've got a much larger multiplier. And so that's where the structural mass comes into play. And I would just say part of the reason it's hard to build an ICBM is again, this notion that as you start to add fuel, you have to lift more mass, the rocket needs to be stronger, the rocket structure has to be heavier, and so as you start to scale things up, you sort of hit diminishing returns, and that's why it gets difficult. If you look at a sort of a modern space launcher, a useful rule of thumb to keep in mind is that it's roughly 90% fuel, 10% structure, and only about 1% payload. The other thing that the rocket equation does is it explains why you want to go to multiple stages. And so here's a simple example that tells you why it helps to break a rocket into stages. Look at a missile with a total mass of 111 tons, 100 tons of which is propellant mass, 10 tons of which is structure, and 1 ton of which is payload. And if you just apply the equation I showed you before, you've got the initial mass over the final mass, you get a velocity change of about 2.3 times the exhaust velocity. So now let me take that same rocket and divide it into two parts, a two-stage missile. So I've got the same mass, same total mass, same propellant mass, same payload mass. I've just broken it into stages. And if, again, you go through the equation I had before, you find that in this case, you've increased the velocity from 2.3 times the exhaust velocity to 3.3 times the exhaust velocity. So nearly a 50% increase in velocity just by being smart about dividing things up. And, you know, in some ways it's not surprising because what it says is in the first case, I've got all this structure and I'm carrying all that structure with me all the way through the boost phase. If I can partway through boost phase drop some of that and I only have to accelerate the amount of structure I have left, I can do much better. I think it's useful just to go back and look as an example at the development of Chinese liquid-fueled rockets. Started with the DF-3, which is something like the first stage of the Unha, or the Taepodong 2, although it's more capable in many ways, uses a different propellant, is lighter weight. The second stage, the second step was to put a second stage on that, get what they called the DF-4. They then took those two and put a small third stage on it and got what they called their CZ-1, or their Long March 1 space launch vehicle, and that was what put China's first satellite in orbit. This is sort of similar in size but more capable than North Korea's Unha launcher, again because it was designed in a better way. The point I want to make here is that even by the time they had gotten to the CZ-1 and wanted to take the next step to build an intercontinental range missile, their long-range missile, they scaled the whole system up again. So in going to a militarily useful rocket that could carry a larger payload, again, they scaled up their launch vehicle to the DF-5. And the point there is just that people talk about how useful the North Korean Unha launcher would be as a ballistic missile for long ranges, and you find that it's relatively, it's capable, but it's not for carrying larger payloads to intercontinental range distances. It's fairly limited, and you can see that in the Chinese case they ran up against the same thing, and the result was that they developed a considerably larger missile for their first ICBM. Let's talk about guidance and control for a minute. If you talk about artillery shells and very short-range missiles, they don't have internal intelligence. They're just aimed by pointing them. And let me just say that guidance and control is a part of missile accuracy, but it's only one part of missile accuracy. It's also affected by reentry and some other things, and I'll come to that later. But a guided missile needs, first, a way to steer itself, a way to control the direction of the thrust during boost phase. It needs to, during flight, know the missile's location and its velocity so that it can know where it's going, how fast it's going, and what it needs to do to maneuver. It needs some sort of computer on board to know when it's reached the velocity, angle, and altitude that it needs to shut the engine off and allow it to reach its intended target. And it also, when it reaches that point, needs a way to try and terminate thrust. So let's talk about each of these briefly. A very common way to steer on early missiles, this was true on the V2. On the left here, you have the back end of a Scud missile. On the right, you have a back end of a DF2, an early Chinese missile. And what you can see is they steered by having what are called jet vanes. There are surfaces that actually stick into the exhaust coming out of the back of it. And by rotating sideways, you send some of the thrust laterally, and that causes a sideways force, which causes the missile to steer. Now, this is actually a simple, tried and true method, and it's been used for a lot of different systems. One of the disadvantages of it is by having something sticking into the exhaust flow, it actually tends to decrease the thrust by a certain amount. And so this is a system that has been used a lot, but as countries are trying to get longer and longer ranges and get all the advantages they can out of a system, they try to go beyond this. In fact, one of the interesting surprises when the South Koreans discovered debris from North Korea's satellite launch on the Unha was that the Unha no longer uses jet vanes. That, in fact, what you see here is the four large engines. This is looking at essentially a schematic of the Unha from the back. And you see these four large engines. And then in addition to that, they had four smaller engines, which are in green here, called the steering engines. And so instead of having jet vanes stick in the exhaust and give you some lateral thrust, by differentially having thrust on these steering engines, you can change the direction of the missile. Not only do you not have the reduction in thrust due to the jet vanes, but you actually have some increase in thrust due to the fact that you're getting some thrust out of the steering engines. So this was something of a surprise to realize that North Korea had done this. This kind of thing has been done for a long time, so it's understood technology. But it shows, again, the kind of evolution as people are thinking about how do I eke more and more capability out of these systems, what kind of thing do I want to do. This is also the kind of thing that's used on the Musadan, certainly on the Russian submarine launch missile that it's based on. And finally, the direction that people tend to go with more sophisticated missiles is what's called gimbaled nozzles or thrust vectoring, in which case the nozzle itself basically can rotate in various directions, and so it's a simpler system, and it's the kind of thing that's used in most current systems, most U.S. and Russian and Chinese missiles. So the question then is, how does the missile know its speed and location? One early system that's used is that it can be radio controlled. So you can have off-board control on the ground that is communicating with the missile as it flies by radar. And this is a missile that a picture that I took in China of a DF-2A, and you can see at the front end are these little antennas which were used to speak to the ground radar, so the missile was sending back information, calculations were being done on the ground, and then control messages were being sent from the ground. More typically what you do is you have what are called inertial systems. Accelerometers can be put on to sense both the rotation and the acceleration, and you can have an onboard computer that integrates those to calculate the speed and the location along the trajectory. You can either have what are called strap-down inertial, which means accelerometers that are fixed to the body of the missile, or you can have what's called a stable platform. So you have a platform with gyroscopes, and as the missile starts to turn, the table keeps its orientation in space, and the amount that it has to shift to be able to keep that orientation is interpreted as telling you something about the operation of the missile itself. You can get good accuracy if you have very good sensors and a good computer that can do these calculations. One of the things that's used for modern missiles to get even better accuracy is they will do star sighting at some point. So during boost phase, they'll integrate up the signals they're getting from their onboard sensors, and then at some point you want to calculate, how sort of take the error out of that, and so they can actually do star sighting where they look for the position of a given star, and that will allow them to recalibrate their position. The other possibility is using a global positioning system data. That's certainly possible. There's always been a concern about whether or not that could be jammed, and so there's been a tendency for military missiles to try and use systems that don't rely on outside signals, just so that can't be denied to them. I just want to point out again that when you're talking about guidance and control, remember that it only occurs during boost phase. And again, it's like throwing a baseball. Once that first couple minutes is over, you have to have aimed the missile properly in order to get it to reach its target. As I said before, one of the other things that you need to do is once your onboard computer has taken the information about where the missile is, how fast it's going, it then keeps calculating what speed and direction and altitude do I want to be able to reach my target. When it reaches that point, you would like to shut off the thrust so that at that point it heads toward the target. For liquid engines, you can shut down the propellant flow, so you can shut the engines off. It's more complicated for solid missiles, which I may be able to come to. But that needs to be done very carefully in order to control the speed and the burnout angle precisely. And especially for long-range missiles, if you can do sensitivity analyses and you can convince yourself that if the angle and the speed are uncertain by a certain amount, that by the time you propagate that error over mid-course phase and down into reentry, that can lead to relatively large inaccuracies. And so typically what you will do with a liquid fuel missile is you'll do it in two stages. You'll first drop the thrust level to sort of 5% of the full level. That gives you some fine control, and you can fine-tune the speed and the altitude, and then you terminate. So again, that's a step that you go through to try and control the termination of the thrust. Now, at the end of boost phase, for longer-range missiles, you want to separate the warhead from the empty missile body. And the reason for that is that once the missile burns out, the range is the same whether or not the empty body is attached to the warhead or not. I mean, that's just the Galileo principle. But when the missile begins to re-enter, the atmospheric drag that it encounters will put strong forces on the body. And if the range of the missile is over about 400 kilometers, the speeds are high enough and those forces are large enough that it will break the empty fuel casing off of the warhead. And when it tears off, that can result in forces that disrupt the trajectory, both because the process of that happening can cause the warhead to spin, but also if it breaks off and doesn't do so cleanly, now you've got edges and rough metallic flanges that can cause problems with the atmosphere and atmospheric forces as you go in. And that's in fact what happened with the stretch Scuds, the Al-Husseins that were fired by Iraq against Israel in the 1990 Gulf War. It caused, when these tanks broke off, it caused spiraling of the warhead, which made them essentially impossible for the Patriots to hit. So it was both an inadvertent countermeasure, but it also made them very inaccurate. Let me turn to reentry then. As a warhead reenters the atmosphere, again, we're talking about sort of below 100 kilometers altitude. Atmospheric drag begins to slow the warhead. Kinetic energy of the warhead is transformed into heat of the air, and some of that is transferred to the warhead. Now, if you think about it, the kinetic energy of a 1-ton warhead traveling at 7 kilometers a second is as much energy as released by about 10 tons of high explosives. Now, that's not surprising because you just use tens of tons of chemical propellant to launch it into a trajectory that has that speed. But what it means is that it's got a tremendous amount of kinetic energy, and that, as I said, as it slows down in the atmosphere, that gets transferred into heat. Now, because of that, early on, scientists weren't sure that you could actually launch a person into space and get them back alive, that you could deal with that tremendous heat load on the way back. And so that's one of the things that has to be dealt with. What they realized was that if the drag of the warhead is high, then most of the heat is generated at high altitudes. In other words, if the drag of the warhead is high, it will begin to slow down at high altitudes, and the heat. If the heat is generated at high altitudes where the atmospheric density is small, then the amount of that heat that's transferred to the warhead will be relatively small. And this reentry phase and the heating is controlled by what's called the weight-to-drag ratio, the ballistic coefficient, which is given by beta. So you can see it's basically the weight of the object divided by the drag coefficient times the cross-sectional area. So what's important to keep in mind here is that a high value of beta means low drag, and low drag means high speed during reentry. Just to give you an idea of how this affects reentry speed, here's a graph that shows speed of a reentering warhead versus altitude at two different values of beta. It's coming in at about 7.2 kilometers a second, so there's an intercontinental range missile. The upper curve is for low beta. Beta tends to be given either in engineering terms of pounds per square foot or in metric terms of newtons per square meter. And what you can see is if I've got a high drag or a low beta warhead, it starts to show noticeable deceleration at about 60 kilometers altitude. By the time it's down at about 10 or 12 kilometers altitude, it's essentially reached terminal velocity, and the velocity and the speed doesn't change much after that. On the other hand, if you have a high beta warhead or a low drag warhead, you can see that the speed isn't affected until you get much lower in the atmosphere. And then, in fact, by the time it reaches the ground, it's still going 3 kilometers a second, and it has not reached terminal velocity. So this is worth keeping in mind, that the value of beta is related to how high in the atmosphere you start to get serious deceleration, and also the speed at which it will hit the ground. So let's then talk about how that affects the heating rate. Well, the drag on a warhead goes like rho times v squared divided by beta. So it depends on the square of the velocity and the density of the atmosphere. And again, for a lower beta, that means higher drag. It slows at a higher altitude where rho is small. The heating rate, on the other hand, goes like rho v cubed. And so if v is low by the time it gets to high density parts of the atmosphere, you'll have less heating of the warhead. And here's an example of it. So if you look at this shows heating rho v cubed versus altitude. On the left part of this graph, you've got a high drag, low beta warhead coming in, and you can see it's logarithmic, and so the heating rate you can see is much lower than it is for the high beta warhead that's on the right side of the graph. And you can also see that the altitude of maximum heating for the low drag case takes place at a higher altitude, and that's simply because at lower altitudes the low beta warhead has slowed to the point that the V cube term is smaller. And if you actually integrate up the heating on these two cases, you'll find that the heating of the high beta case is about 30 times that of the low beta case. And so trying to have a high beta and keep the speed high during reentry leads to a very high heat loading. Now, just to show you how people tried to deal with these things over the years, here's a couple examples of reentry vehicles. Very low beta is the Mercury capsule. This came in with the flat part of the capsule to the atmosphere, so it was very blunt. It slowed down high in the atmosphere. And in fact, if you use this kind of thing, some of the early heat shields were made out of oak, and so this is not a very stressing case. That also means that the winds and other things can affect where it lands. As you may remember, it used to take them a while to get to recover astronauts when they came down because they weren't sure when they were going to land. So in developing warheads, they started to make them more aerodynamic. So for the Titan reentry vehicle, this would come in with a pointy end first, but you can see it's large, it's fairly blunt, and this is sort of a medium value of beta. On the other hand, if you go to something like the Minuteman III reentry vehicle, you can see you go to something which is a very high beta. So it's pointed, it's very narrow, and so the drag on these warheads is quite small. Now, the problem with trying to with trying to go to something that has that's very sleek like this high beta is that you, again, have to build a heat shield that can deal with those sorts of things. If you're trying to build a heat shield that can protect a low beta warhead, you can do that with readily available materials, assuming the warhead is blunt enough. So you rely on putting insulation around the warhead so that you keep the warhead from the hot outer walls of the RV. And again, that's the kind of thing you can do with accessible, with materials that you can get, with good insulating materials. On the other hand, if you want to talk about a heat shield for something like these high beta RVs, it's much more difficult, and it requires specific materials, and in particular, just having insulation is not enough. And what these are designed to do is they have a carbon material that covers the outside of them, and that carbon material evaporates or ablates at high temperature, and so as the warhead is coming through the atmosphere, you turn the carbon from a solid into vapor, and that soaks up a tremendous amount of heat and carries it away from the reentry vehicle. So building a working heat shield is certainly possible. People ask this a lot about North Korea, for example, but it needs to be tested to give you confidence. And the real issue is what's the effect of these different things on accuracy. And so let's turn to that as sort of the final point here. What are the sources of inaccuracy? Well, one that was an issue for a while but is less of an issue now is just uncertainties in the location of the launch point and the target. That's largely been taken care of with things like GPS. Second thing that people worried about for a while was errors in calculating a trajectory due to gravity variations of the Earth. The fact that the Earth is not exactly round, the fact that that the densities of the Earth change the gravity map. Those things are understood better now, in part because of experience having satellites going around the Earth and understanding what happens to their orbits. One of the key things, of course, is limitations of the guidance and control system during boost phase. In other words, how accurately can you aim the missile during boost phase? So one of the problems is the sensors. If there are errors in your accelerometers, how good is your computing? If you're trying to compute the speed and location based on the information from the accelerometers, how well can you do that? How well can you calculate the trajectory that you want to follow to get from where you are to the target? And as I was talking before, errors in thrust termination. Even if I think I know what I want to do, I have to be able to shut the thrust down in a very controlled way. But the other thing that's important are reentry errors. And the reason reentry errors, I think, are quite important is even if you have a perfect guidance and control system, you still have to deal with reentry errors. And that means that while a lot of people are concerned about export controls on things that a country like North Korea might do for building a better guidance system, they still have to deal with reentry errors, and that's an important piece of things. The problem is that there are unknown atmospheric conditions over the target in terms of specific winds, density variations. To try and reduce the effects of those lateral forces on the warhead, you'd like a high beta so that you can pass through the atmosphere quickly, which means that the warhead's less affected by the atmosphere and the forces have less time to act on it. But there's also problems with you can have unpredictable forces that are created by the warhead. For example, we think of a warhead coming in perfectly aligned aerodynamically, but what if it's not? What if you have what's called an angle of attack? So it's an angle between the axis of the warhead and the direction of motion. Well, all of a sudden you've got a lateral force which can get very high at high speeds because of atmospheric forces. You can also, if that happens, have corkscrewing, so that instead of coming straight down, that angle of attack will corkscrew around the velocity vector. You can also have asymmetries on the reentry vehicle. If you have, a dent on the side of it, a rivet on the side of it, something that's asymmetric, again, as a rho v squared, which is those lateral forces go up, you can have very strong lateral forces that are going to affect the accuracy. And a particular problem with high beta warheads is that you have this ablative coating for heat shielding, and it's very difficult to have uniform ablation. It's one of the things that the United States and Russia spent a tremendous amount of time on when they were developing ablative coatings, was what can you do to try and make this ablation occur as uniformly as possible. And because if it doesn't, then again, you're going at very high speeds, you've got asymmetric forces, and that can pull the warhead off your intended path. Now, to reduce those, you can do things like, take care when you release the warhead, you can spin stabilize it, and if you have it spinning as it comes into the atmosphere, then that will tend to average out some of these lateral forces, but you still run into problems. And so the bottom line is that reducing these kinds of reentry effects is very difficult. If you think back, as you increase the range of the missile, the guidance and control errors increase because you've got a longer time for any inaccuracies to build up. And as the speed increases for longer ranges, the reentry errors increase. And so again, part of what I was saying is that people talk about the importance of guidance systems and getting better guidance and control, but it's worth remembering how important these reentry vehicles are. Just to give you this definition, the way that missile accuracy is talked about is called the CEP, the circular error probable. It's the statistical measure of accuracy. It basically says it's the radius of a circle that's centered on the mean impact point, which is called P here, that includes half of the impact points of the missiles. The distance P, which is you calculate the mean impact point, that may not be the point that you're actually aiming at, and so the distance between the mean impact point and your aim point is a measure of systematic inaccuracy, and it's called the bias. Some typical CEPs, again, for Scud B, short-range missile, typically people say about 1 kilometer. By the time you get from 300 kilometers the Scud up to about 1,200 kilometers the Nodong, as well as the faster speed of the Nodong coming in through the atmosphere, my estimate is that you're probably up around 4 kilometers, and that's assuming that the warhead isn't tumbling or doing anything dramatic. If you look at the first Chinese ICBM, the DF-5, estimates of the accuracy of that were something in the order of 1 to 3 kilometers. And then if you compare that to a modern Trident II submarine launch missile, we're talking about the numbers that people usually talk about are in the range of 50 to 100 meters. And so at that point, you've worked very hard to do as well as you can on guidance and control. You've mapped out the gravity field of the Earth, so you know what to expect when you're calculating the trajectory. You've got a very high beta warhead that is as symmetrically controlled going through the atmosphere as it can be, and you're trying to use what weather reports you have about the target to try and take into account whatever you can about the conditions around the target. In terms of terminal guidance, let me just finish with this. One of the problems with terminal guidance is you have to be able to have a mechanism to steer the warhead. There are various things that people have used for that, including sort of shifting an internal mass in the warhead, which would allow you to control some of the lateral forces. You also need to know where you are. You can get GPS updates before you start to re-enter, but if you have a missile that's over several hundred-kilometer range, you tend to get a plasma sheath around the warhead as it's coming in because of heating the atmosphere, which can make it difficult or impossible to get GPS signals. So depending on the situations of reentry, you can't necessarily rely on GPS. So people often talk about terminal guidance. Again, it's relatively straightforward if you have a way to maneuver to get an update before you start to reenter, but actual process of trying to terminally home on a target on the ground at high speeds can be quite difficult. So let me stop at that point and see if there are any questions or comments. Let's see. George had a question here. Said, can the steering engines be used after the main engine burns out? Well, the steering engines would be powered by essentially by the main engine. You could presumably have a secondary pump and combustion chamber, so you might be able to do that to some extent. I don't know whether that's the system that North Korea used on its Unha or not. Iqtidar. Oh, wait a minute. Stephen says, if your estimates about the Musadon are right, why are we worried about it? Well, the concern about the Musadon is a couple things. There are claims that people have seen engine tests. And so one argument is that it may be ready at some point in the near future to actually flight test. But the bigger concern is that if the Musadon were flown, or if the engine were really tested and North Korea had some ability either to build them or had a number of them, that because it's a more capable engine, you would be able then to upgrade the capability of the Unha, which currently relies essentially on no-dawn Scud technology. On the other hand, by going to something like the Musadon engine, you would essentially you would upgrade to something like the Chinese DF3 or DF4, which is, again, are more capable than the Unha stages. And in that case, in terms of an ICBM, as I showed in the Chinese case, they still went on to develop a considerably larger ICBM. So the concern about it really is that it's a stepping stone toward more capable missiles, but the Musadon in and of itself, I think, would not be, it's really the implications of that for future things than the missile itself. Let's see, did Iqtidar have a question? I don't see it here.
You can unmute him, maybe? We could unmute him.
Whoops, I don't see him on here. I wonder if he
You are no longer muted.
I unmuted
Right.
him.
Iqtidar?
Can you hear me, David?
Oh, Iqtidar?
Yes,
yes,
I can.
Can you hear me?
Yes, I
Yes.
can.
Right. So let's say in case I don't consider the drag effects and my warhead is in its re-entry phase, how significantly does the drag affect the impact point, the intended impact point of my incoming warhead? So if I assume that,
Yep.
If I assume, yes, sure, go ahead. Yeah.
Well, I was going to say, so there's a lot of things that can happen. Let's see, I'm hearing, I'm going to mute you for a minute here because I'm getting, there we go. One thing that can happen is that during reentry, you can get the warhead to start to tumble, you can get the warhead to start to spiral. Those can lead to, kilometers of error at these high speeds. If you're talking about a warhead that's coming in relatively well behaved, again, it can depend on winds, density variations that it's going through, and you can again get sort of kilometer of inaccuracy. The estimates I did on the NODON, where I got about 4 kilometers of accuracy, assumed that it was a warhead that was coming in fairly well behaved, and I looked at different sort of atmospheric conditions and tried to look at how those would affect the accuracy, and in some of those cases, I was getting 2 to 3 kilometers just from these lateral effects due to the atmosphere. And remember, the NODON is coming in at maybe 3 kilometers a second. So by the time you talk about a much longer range missile, if you increase that to 6 kilometers a second, so it's twice the speed. That's 4 times the lateral forces due to just the square of the speed. You start to get you start to get very high inaccuracies. Does that answer what you were?
You are no longer muted.
Thank you, David. Thanks.
Mm-hmm. All right. Well, we're running a little long here, so I think I'll pull it to a. I think I'll pull it to a close. As I said, I will post these the slides along with the recording the presentation if anybody wants to go back and look at some of the graphs and things like that. So thanks very much for joining us, and we'll send you a notice for next month's talk. Thanks again.